Yeah. So again, my name is Fardad. My office is DB 1037. If you want to come to the office, you have to, you know where the bridge is, where it connects the two buildings together? If you go on, like under the bridge, if you get into the TEL building or DB building from that, under that bridge, at your right-hand side, there's this glass area called CDOT, Center of Development of Open Technology. It's a glass door. You open the glass door, you turn right, and you keep going. You're going to see some booths and stuff. So you keep going, and then at your left side, you see room T1037. Okay? And that's where I live. This is my schedule. So as you see, everything happens from 1:30 to 3:30. I have 2 office hours over there at between 11:40 and 12:30. One on Monday, the other one on Tuesday. How many people have classes during that time? Both of them, not one of them. How many people? And one thing I have to tell you before we start, please let's have it's what we call a full duplex communication. Long time ago, like if you get when you get your data communication scores, you're going to see there are 2 different types of communication. One is half duplex, the other one is full duplex. Half duplex is like you're listening to the radio. The person who's talking on a radio has no idea if you're listening to him or not. All right? But two-way communication is like talking on a ham radio. Whenever somebody says something, Roger, over, so you keep telling to each other yay and nay so you understand if you are actually talking, if the person got your message or not. Okay, I want the latter. I want full duplex communication in class. So when I say, how many people have classes during that time, don't do like this, you know. Don't worry, nobody's going to shoot you when you put your hands up, so just do like that. And I want responses, actually, from the students. And my class is a little awkward when it comes to teaching, so I teach using you guys, which means I'm going to ask you a question, and this gentleman is going to try to answer. If he can't answer, fine, he answers. I use that answer to go to the next topic and the next person, and it keeps going like that. If you don't know the answer, if you're not in the mood to answer that, then you simply say pass, and it goes to the next person. Okay? I start from random places, and I keep asking questions like that. Like that, I try to keep you involved. Computer science, computer program is a very dry subject, boring subject, puts you to sleep unless you really want to learn it. Okay? If you love computers, no, you're not going to fall asleep. But if you're here just to make money, then you're not interested. You like to be an artist, but now say the heck with it, I'm going to be a programmer now. So if that's the case, I'll try to be like a clown, jump up and down, dance sometimes if I have to kind of keep you awake. All right? So again, now full duplex. How many people have classes both days on those days? One? The green one, the office hours. I want to just put the office hours at the time that most of you have time to come if you have any question. Oh yeah, my apologies on that. There you go. Monday and Tuesday between 11:40 and 2:30. How many of you have classes during that time and cannot come? I saw 1, 2. Okay. Okay, so which day you can't come? Monday you can't come. Both. If you cannot come, both of them. If you can come on one of them, it's fine. Okay, both. How many people on Wednesday, same spot, cannot come? Good. So I'm going to move them. You said Monday? I'm going to move the Monday to Wednesday. Okay?
Yeah, I just found out that I both. I'm sorry. I just checked.
How about Wednesday?
Yeah, Wednesday's fine.
Wednesday's fine. Beautiful. So Wednesday's fine. All right, so I'll move it to Wednesday. So we'll be fine. But as the time goes going to pass, you'll see that those office hours that I'm going to put over there, it's guaranteed that I'm in the office, and you don't need an appointment. You just drop by. But because of that fact, if there are already four people over there, you know, you have to wait, and sometimes you won't be able to. Okay? So those office hours are guaranteed that I'm there, and if I cannot be there, as I send you a message, if there is a class cancellation, I'm going to send you an email telling you that office hours are canceled at this time. I cannot be at the office. So I am there. If I'm not there, you'll know. Okay? If you can't come during those times, book an appointment. Send me an email for that. I need to see you. We need to talk. I need help in this and that. And we set a time. We find a common time. And I'll come in. So those office hours are guaranteed that I'm going to be there. Any other time you pass CDOT area, I'm in the office, knock the door. Can I come in? But again, if I am busy, I'm going to say, no, don't get pissed. Okay? If it's not during office hours, it means some other priorities might be there. But if it is, if I am available, no problem. Just knock the door and drop by.
Sorry, Professor, to bother you again. So
Professor, my name is Fardat. Professor needs to have a PhD and have a chair in a yada, yada, yada. And my name is Fardat. Fardat will do.
All right, Fardat. So you're saying Wednesday from 12:30, same like the green?
Yeah, exactly.
Slot, all right.
Yeah. You'll see. I'm going to move it. I'm going to make it. I'm going to update it.
Right.
Okay, I'm going to update it. You'll see it. All right? So, My Seneca is a place that you're going to be a lot, and these are your subject. If you look at them, it's not available now because I want to put all the columns and everything. So let me just make it available now. But it doesn't make any difference. You don't have any computers right now. But anyways, you got to go over there. You've been on My Seneca, right? Hopefully. If not, please log in. And this is the first thing that I say. So the announcements that I put over here, a copy is sent to you via email. I do not accept any emails outside of Seneca. So if you're sending me an email, cooldude@gmail.com, that's not a thing that I want. It has to be from your Seneca email. If you know how to impersonate your Seneca email account, do it, that's fine. If you don't know what I mean by that, then it means you don't know. Okay? So use your Seneca email for communications. Okay? Because you have your student ID, like your email ID over there, and from there I can quickly recognize who you are, and so on and so forth. So email, when you're sending an email, the only thing that is read over there is this, and I want you to please follow it. Very important. Very important. Subject line of all your emails must start with IPC144-. Why? If I open my email, you're going to see I have an inbox with 95,000 email in there, right? And I want to be able to prioritize when I have students sending me something to be able to reply quickly. So I have a filter that if it says IPC144, it drops it over there, so I'll be notified that I can reply quickly. If you don't put IPC144, it's going to go shuffled between thousands of emails and spam and advertisement and things like that, and hopefully by the time you graduate, I'll see it. Okay? So again, that's the only thing that I ask you to please do when you are sending me an email. Write IPC144 at the beginning of the subject line. Okay? Just write IPC144- cannot come to the test. IPC144- I have problem in assignment 2. Another thing that I did not mention over there, I'm going to mention over here right now, you are in college now. Act like a college student, not a 13-year-old boy or girl. Which means when you are sending an email, have etiquette. It's not that I expect that I feel offended, but it's just not right. Go to your accounts, create a signature for your email. Your name, your student number under each email that you're sending. Learn these things because you're going to need to do all these things when you're going to a workplace. And those people who are already coming from workplaces, my apologies to mentioning you these, but you just have to. Okay? When you are sending me an email, to send me an email, don't try to find just one email and say reply to that and sending me an email. So the subject line is, I have problem with assignment 2, but the body of your email says that I cannot come for exam. Okay? The subject line of your email must relate to what you write over there. And things that if you don't put subject in your email, don't even think about me answering it. So so be professionals when you're sending an email. Okay? Be a grown-up, an adult. Okay? And that's very important. I don't expect you to have perfect grammar over there since I don't have one. Okay? My English language is fourth language for me, so I'm a Canadian like most of you, so you know how it goes, right? So keep that in mind. Again, office I mentioned, the phone number is right there. The schedule over here, if you click over here, you're going to go to that c.wiki thingy that we opened. Subject outline is where you see what we are going to do on a weekly basis. This is a suggestion of the things that happen, but teaching a class is a dynamic thing, and because it's a dynamic thing, sometimes I jump over topics back and forth. So I can't guarantee that that's exactly what it is, but I'll try to make it as close as possible. Rarely happens that it doesn't go with that. But for example, the logic section that you see over there, that logic section is going to get spread around everywhere. It's not going to be only in half a week, okay? It's going to be everywhere. So you're going to see it over here, and you're going to see links over here with workshops and everything that you see. Because of the strike that we were in, the semesters have been reconfigured. So few things that you see in here may change. So keep that in mind. If you see it once, don't save it on your computer and think that you have the website. Take a look at the announcements and things that you see over there. So, where was I? Subject material, like the things that you need to have, is on a place called GitHub. What the devil is a GitHub? GitHub is a company who hosts Git repositories. Okay? Git is a software whose job is to keep track of your work while you're doing it. The most simple, it's a version control system. The most simple one that you've always used is the keyword, the button undo. When you do undo, what happens? It takes you step by step back, right? GitHub is Git. The Git software is 1,000,000 times more sophisticated than that. So the changes that you are doing and things that you are saving and all those things, it keeps track of everything. It says that January 15, your work was at this stage, and you do lots of stuff. It says, shoot, I made a mistake. I want to go back and do something. So you can actually say, I want the status of my repository to go back to this thing, and you start at. So it takes care of those things. Or if you want to add a feature to something that you have, you're writing a book and you want to add a chapter to it, you can branch your project into two things, start editing the new chapter in your book, and when you're done, you say merge it back in. So it merges everything back in. So while you are doing the editing, the original book that you have written, but don't get scared, you have nothing to do with these things. Okay? This is just, I'm telling you the capability of Git. I have no idea how it works. It's that complicated, but I'm using it. Okay, so GitHub is a place that we put all this stuff. Why? Because it has repositories and I can update it and everything's going to go over there. A place that you're going to be at a lot. I'm going to sign out, or let me actually go using another browser that I'm not logged in with. Because I'm logged in and I'm the owner of the repository, you will see it from my point of view, which you are not supposed to. You are supposed to see it with this view. Yeah, there you go. These are the repositories that you see. IPC notes SNQ. I'm the only prof that actually puts the notes up there. So as I do anything in here, as I write anything in the class, or any notes that you see, any program that you see, immediately goes to that repository. So if you open up that repository, you will see this is your section, another section, you go to this one. It's like a directory structure, and in here you will see stuff. You will see the first one today. I'll create a program for you and I'll put it up so you'll see. So anything that you see I'm doing on the board, you don't need to write it down. Although I encourage you to do so, because writing, you will see, is one of the most important factors of putting something in your permanent memory. So if you do it, I bow to you. People with computers, that's not writing. Although we all love to do that. We all used to be high-tech and stuff like that. Punching the keys on a computer and taking a note won't work. As a matter of fact, it's a big distraction. So many times when I see that the students are not at the level, I ask everybody to close down their notebooks. I'll tell you when. Don't worry, I'm not talking about it. I see you are the only one who has the notebook open. So sometimes I see I'm teaching and somebody is looking at their screen and go, it means they are watching something over there, like a joke on Facebook or something on Instagram, right? So I don't want that, okay? Well, I want your full attention when I'm talking. And that's the most important thing. When I talk, everybody's quiet. That's the only thing that I ask you to do. I don't want you to call me sir. I don't want you to respect me in any way. I want you to be like a friend with me. But there's only one rule. When I talk, everybody stops talking. Okay? Unless you are having a heart attack and you want me to call 911. That's okay. All right? So it's going to be all over here. So, and you're going to see online. You're going to see there's a README over here, and a README is specifically in each. So if I go to this section, SNN, come on, you can do it. There is a README section specifically for section N, and if you go to the Q section of that one, and there's a common for both over here. So things that I want my both classes to know goes over here. If there's a specific thing that I want to put for you guys, it goes in yours. One of the things that you need to do that is very important is to create a GitHub account. By the way, that's supposed to be a C. I barely write, so you're not actually. Let me just do something else. Just a second. Where is it? So create a GitHub account. Create a GitHub account and register for their student offer. Okay? And these days, please don't tell me, how do I do that? Write GitHub student offer. It comes up. So what happens, GitHub is an organization that works as its goal is to have everybody's project on the same place on planet. And the projects that they are doing, if they are open source, it's free. What is open source? Remember, either you know the answer or you simply say pass. Okay? What is open source? Anyone can look at it, and because of that, they can improve it or use it or share it or edit it or if you hear 3 passes, it means you can come to rescue. Okay? But let me tell you, so open source has had all the things that you just mentioned. Okay? You can share it, you can see the source code. One of the most common things, one of the most common open source projects is Chrome. The Chrome browser, you can actually go download its source code and take a look at it and see how it's done. You can actually get the Chrome and call it Jack and, and republish it if you want to, because it's open source. You can do that. Of course, you won't be able to update it as often and make it as good as what Google does, but that's why you're not going to be able to do anything with it. But you can use its platform to have your applications with it. You can use its whatever many features to do whatever you want to do with it. Because of that, open source is very difficult to have. An open source project is very hard. It's very difficult to have problems in it because all the people on planet are eyeballing it. It's not like a section of a company that actually looks for bugs and stuff. Everybody's looking at your source code. Okay? The biggest open source project in the world, anybody knows what is that? Linux. The most powerful operating system in the world is open source. Okay, and that's why you have so many different flavors for it. You have Ubuntu, you have Mint, you have Debian, you have so many different flavors of Linux. You have Fedora, you have Red Hat. Red Hat is kind of a Fedora with support. But anyways, so GitHub as a company, what it does, yes?
I'm sorry, I could not find the
link account.
GitHub account. Didn't find a link for it on your page.
Oh, we'll come to it too. I think there is one over there. My account. It's not my account, my friend. These are repositories. Yeah. So what happens is that did I send you an email? Did you get my email?
I did.
In that one, do you have the one that says subject material GitHub Seneca 144100? If you click on that one, ta-da. Oh, okay. My apologies. Well, anyways, so all right. So GitHub has all the people put their projects over there and so on and so forth. Now, because it's an open source thing, it wants to have all new programmers to know it and use it. Because of that fact, it will give you free accounts for it. Accounts to be able to have private repositories for it. If you have an open source repository, it's free. You can have 50,000 repositories in there. Nobody cares. Nobody's going to charge you a dime. But if you want to have a private repository where nobody can see, then you have to pay them to do so. But for students, it's free. Not only that, they give you licenses for so many softwares out there for the duration of your education. My sincere apologies on this. I have to have my cell phone on because I have a situation that I have to be always on call. So I apologize for every now and then this thing ringing. I'm just going to take a look at it, see if it's that call that I have to take or not. And then, so my apologies. That's something that I cannot. But your cell phone should be off. Okay. Unless you have an emergency like me, like I have a father that I have to make sure that he's okay. Anyway, so what I was saying was that you can get all these things and immediately do that. So that's one of the first things that you need to do. Create an account on GitHub and register for their student offer. Go on GitHub and you'll find out how it's done. Okay? That's one of the most important things you need to do. Activate your Matrix account. Everything happens on that cluster. Anybody knows what's a cluster? What's a cluster? What's a cluster? What's a cluster? Nobody knows what's a cluster? Okay, a cluster is essentially a computer that is made up of computers. So you have a computer, it has one name, you get connected to it, but behind the scene there are 50 computers together working. Okay? Like Matrix. That's the name. See? They put it after the movie network, Matrix. So it's Matrix. It's a series of computers connected to each other. It's a huge Linux platform. Everything happens through that computer. So you have to have an account on that one to be able to submit your work. You have to have an account on that one to be able to test your programs, final test your programs. So activate your Matrix account. How to do that? Go to the Learning Commons, the people sitting over there and helping you. You know what I'm talking about, where all the computers are in this building right down in the first floor. You go over there and help desk and say, or simply send an email to helpdesk@senecacollege.ca and I want my Linux account activated. When you do so, then you can use your Matrix account. If you have a computer at home, make sure you install PuTTY on it. PuTTY is a telnet client. It's a terminal client. That with that one, you log into Matrix. So you essentially go on PuTTY and you put matrix.senecacollege.ca, you connect to it, then it asks for your user ID. That's your email ID, whatever your email ID is. And then your password, that's the password that you log into Blackboard to MySeneca with. You put that one and you log into Matrix. Okay? You need to have that one activated. So these are the things that you need to do. Very important stuff. I'm going to write these things one by one, and I'm going to put it on GitHub so you know where it is. Okay? So I'm just saving this. I'm going to say save on this PC, and I'm going to go on this PC, and I'm going to go to Seneca, IPC144, notes, we are SNN, and in here I'm going to say 012 do, and I'm saving it. Okay? So it's going to be saved as a Word document in that repository, I'm just going to demonstrate how it happens. So I'm halfway through right now. I saved it, right? So I'm going to go to that directory that I just saved it in. You're going to see this happening every single day. So in here, I'm going to say git add. So it's going to ask me, would you like to add the to-do? I don't want the temp one. I just want that one. I'm going to say OK. And I'm going to say commit. And in here, I'm going to say initial to-dos. And I'm going to say commit. And finally, I'm going to say push. And this push, it means from my computer goes to Git. Sorry, let me pull first. I made some changes that I have to apply to mine. Now I'm going to say push. Yeah, so now it's pushed and it's right up there. Now if you go to SNQ, SNN, you see initial to-dos, and you go over there, there is the Word document. Okay? And I'm going to convert it to PDF too. I'm going to tell you exactly how to bring everything on your local computer and everything. It's going to be explained. So you'll see that anything that I do, it goes right on the web, and you have access to it. Not only that, right now that I'm talking right this, I'm actually recording it. So I'm going to put this on YouTube. And what happens is that when you go over here, lecture videos, you're going to see the video of the lecture is over there if you want to review things. But not in a second think that because it is there, you don't need to come to class. Okay, I take attendance every now and then, okay? And that's for me to judge later on to see if I see, you're free not to come to class and get your A+ and pass, okay? But if you don't come to class and you get 49% and you ask me to please pass me, then I'm not going to pass you, okay? Or if you have a B+ and you want to make it A, or you have something like that, and I'm not going to do that, okay? I only help those people who come and attend the class. It means you are actually participating, okay? So it's going to go over there. Lecture videos are going to go over there. The link for it. Yes?
I'm not acquainted with GitHub, but is there a way to commit through the terminal? Do you have to do it graphically?
No. No. You can do it. Git is not graphically at all. Git is all command line, which brings us to the next thing. Git. Pro Git book. This is an online complete reference to Git and its comments. I recommend reading chapter 1 and 2 and glancing to chapter 6. Okay? If you do that, you know Git more enough for you to take you through the whole program at Seneca. It's 2 chapters, 2 small chapters, each one like 20 pages. It gives you all the commands, all the things. You are not doing any committing. It's me. Only I do it. The only thing that you do, you just get it. Remember. Okay? Although I'm doing it, I showed you that I'm doing that, but you are not. You can, of course, learn it and use it for your own thing and throw away that stupid memory key that you carry with you all the way. If you actually create a private repository on Git and keep having all the stuff that you are doing for school on that one, you don't need to carry that memory stick anywhere. Whenever you're coming to school over here, you go on the Git and you simply say Git clone. It clones your repository on the current computer. You do your work with it and you say commit, push. It puts everything back over there. You delete it. It's a Dropbox on Boost, okay? Git is a professional type of a Dropbox. Let's put it that way. Let's put it this way. If on your resume you write, I know Git, it's going to be around 20% more chance that you get hired. And I'm not joking. Okay, I'm not kidding on this. Okay? For those people who have Apples, okay, Apple products, sadly, you need to do your stuff on Visual Studio, which means either bootleg it, put Windows on it, or create a VM machine on it and install Windows and Visual Studio. You need to have Visual Studio, unless you come and do your work at school. School has Visual Studio everywhere. Visual Studio is one of the most important development tools in the world. And I don't want to take sides to say use Xcode. Okay? You can use Xcode if you want, but you need to know Visual Studio to pass through several different features that we are web programming and things that we are doing in Seneca. And this is a good time to use it because I'm using Visual Studio for kindergarten stuff. Okay? When you get to the point that you have to use it, really use it, you are familiar with it, so you don't waste time on it. But if you don't use it and go to 4th semester and suddenly you want to start over there, you're going to fail the subject because the guy is just creating a project doing this and that, and you're saying, what? Which button? What? And then that's going to be trouble. So use it. Yes?
Could I be using a different IDE?
That's what I mentioned. You can use Xcode if you want to, CodeLight if you want to, Eclipse, whatever you want. Okay? But your assignment gets submitted through Matrix, and I'm not a professional thing. First of all, Apple products is against my religion. I don't like it. They're bully. I don't like a bully company. Okay? I don't like them. Sorry. Okay, that's me. I'm open source. I use Android and I use, I don't know, Linux, and I'm using Windows because it's been there forever since I was 10 years old. Okay? Apple, I just don't like the company, so I don't use it. But if you come with a problem with your code, I'll help your code. But if you tell me, I don't know how to compile an Xcode, I'm saying, too bad, I don't know either. Okay? The thing that I can help you with, I can help you with Visual Studio, I can help you with most open source IDEs, Eclipse, CodeLight, whatever you bring. Okay? That's fine, I can find a way to do it. Apple, I don't know, I don't know how to. If you come and teach me, if you know how to do it, any of you come and teach me. I have an Apple computer in my office gathering dust. I can put Xcode over there and learn. I'll appreciate it. But I
Just had Linux in the core of its system.
Of course it is.
Right, so why there's a huge difference?
Pardon me?
Why there is a huge difference? Why they're not the same? Like when it comes to visual things.
This is Linux.
Yes.
Windows is nothing like Linux. It's just
Oh, so you
Windows.
can use both Linux and Apple.
No. Okay. The projects that you are running should run on Visual Studio and on Linux flawlessly, both of them. And that's how we show you, that's how we teach you how to write portable code.
Yeah.
Because you're going to run it on Windows, it works perfectly. Then you put it on Linux and it doesn't work anymore. Okay? So how to write portable code, that's how we teach it. Okay? But your question was, this is Linux, how it doesn't.
Basically Linux. So
It's not basically Linux. It is a Unix environment. It is.
Yeah.
It's not like it is, actually. Okay? But this is not Linux. Visual Studio is not Linux. Yeah, that may work with Matrix, but it doesn't have anything to do with Visual Studio. Okay, so you have to, and don't be biased against it. If I was teaching iOS, I would tell you you have to know how Xcode works because you're developing iOS. That's not the case. Basic standards of C++, all the things that you're going to do in web programming in 422, INT 422, they're all Windows-based. Okay? .NET is one of the biggest things in the world right now. So you need to know how to work with it. You cannot stay away from it. So I strongly suggest install a VM. Don't install anything else on it. Windows is free for you. You can get everything from school for free with the license and everything. Have a VM on your machine. Install it. It's not going to change your machine. You're going to still use it as it is. And you can use all the platforms as you want. But if you don't want to, you can always come in the lab and do the Visual Studio in the lab at school. It's on all the machines at school. Git already comes standard with Apple. So you through command line, you can clone all the repositories. You can download everything that you want. So your objective is only to be able to download stuff from the website. And that one, you don't even need to know what Git is. All you need to do is to go to the repository and clone or download. You see that? Click over there. You can simply say download zip. And it gives you a zip file. You unzip it, and you're done. So you don't need to know Git. But for your own good, it's a good idea to go through it and learn the few chapters. It's good for your health, trust me. Okay? But for all the GitHub stuff and how to clone repositories, how to get stuff, I'm going to put videos over here. So installing Git on Windows 10, I have a video for it. Install it Tortoise Git so you can do things visually with mouse instead of terminal client. The video is over there. the basic commands of downloading with Git, not with zip. I'm going to put all the instructional videos over there for you too, so you know how to do it. Okay? So the subject is designed in a way so we have maximum outcome in learning and remembering how things are done. Now, this is something that I'm going to show to you, and it's very important. When you learn something, 5% of what you're learning is through what's happening now. Okay? Approximately 5% if you go only through lecture. 10% if you actually read afterwards and go through it. 20% from the visual demonstrations and what you hear and audio-visual or YouTube videos that you're going to go. You're going to get 20%. Whenever I write a program and demonstrate actually how the program works, that brings it up to 30%. Okay? To talk about what I have done in class will bring you up to 50%. If you actually write the code yourself, you go 75%. If you teach your friend how to do it, you go up to 90%. Remember this. These are all studied and proven things. It's not just a, okay? If you are one of those genius people who have eidetic memory and just sits over there and listens and poof, everything is done, I don't know why you're not working for Google now, but hey, you don't need to do any of these, okay? But anyways, next thing, curve of forgetting. This is based on an hour lecture. So when an hour of lecture happens on day one, so you're here and you do this. Tomorrow, you spend 10 minutes for an hour and review what I've told you. Then a week after, you spend 5 minutes to review what we went through. And then 30 days later, you spend 4 minutes to go through stuff. It stays in your permanent memory, long-term memory. You will not forget it. Okay? The course is designed this way, which means you get a quiz. What happens is that I'll ask you to, if you look at your email, it says that anytime you're coming for lab, you're going to have a quiz at the beginning of the lab, a 10 minutes, 15 minutes quiz. And that quiz is about the material I'm about to teach. So I'm going to tell you these topics I'm teaching next day. You're going to go read those things, and you're going to get a quiz on the things that I've never told you what they are. Of course, the questions are very simple. I just want to see if you actually went through it or not. Then I teach it. That's the day one. Then you're going to get a workshop for it. That becomes as an in-lab. So a week later, you're going to get hit with the workshop that is working on it. That's next week. Okay? That's the second day. Then you have at-home section of the workshop. That is 7 days. And then you have a test that is 30 days and a project and assignment that comes that is 30 days after we are teaching. So we try to do this thing via going through repetition of on the things that we are teaching. The course is designed this way. So you try to do it the same way on anything that you do, and just it stays in your mind and you're never going to forget it. So this is something, it's in there if you want to take a look at it. I left it, it's one of the, oh, I closed it. It's one of the documents that I put in here in the notes. Okay, so you can just take a look at them. Next thing that you need to know, IPC project, IPC workshops. IPC workshop is the place that you're going to see the workshops. Okay, we're going to have, it says 10 workshops, but because we don't have time as a regular session regular semesters that we had because of the strike, we lost 2 weeks. So to reduce your workload, we're going to have, I think, 6 workshops or 7 workshops, something like that. And the rest, assignment's going to take over, so you don't get overwhelmed with the amount of work that you're doing. Okay, so on that, probably that 7, 8, 9, 10, or 8, 9, 10 are not going to be there. Okay, keep that in mind. And then you have IPC, the project. Usually, either it's in 2 assignments with 2 milestones. What is a milestone? We ask you to give us something halfway through, so I can make sure that you don't procrastinate and you are on the track. Okay, so if it's a regular project, 1 project for the whole semester, then it's going to have 5 or 6 deliverables, milestone 1, 2, 3. So you go step by step through the project. You don't get lost. We'll tell you exactly what to do. So you finish the first milestone, second, third, and by the time you get to the 5th, you're done. If it's 2 assignments instead of 1 project, then each one of them is going to be 2 milestones or something like that. You'll see. Okay? Yes?
Sorry for interrupting. Off-topic question. You know where the washroom?
Oh, yes. I know perfectly, actually. Go. If you are going now? Yeah. Okay. Actually, let's say break. Give me a second. We're going to have a break now for... Okay, so it's a suggestion from Accurate to install a virtual machine, so you'll be able to actually use Visual Studio. And the good thing about virtual machine is that it doesn't occupy the only thing that it occupies is some space of your hard drive. So you put like 40 gigs of your hard drive, and or 50 gigs, whatever the minimum requirement is, because you're not going to install anything on it other than Visual Studio, Git, and ProduceGit, nothing else. You don't need anything else. And that's enough for you to take you through semester 1, 2, 3, and 4. Okay, so for 4 semesters, you're going to use it. It's not something that I'm going to say for this one. You're going to OP 244, you're going to be in same trouble. 345, same. 422, same. You're going to have the same problem. You have to, if I were you, I would do that. And also, you're a computer science student. Be a geek. Go get it. Find out how to do it. When I say a virtual machine, if you don't know what a virtual machine is, look at VMware. I know there are several different possibilities. Any geeks over here with Mac who knows Mac properly, have installed VMs on it? Okay, what kind of VM comes on Mac free?
You can use Wine. Or you can install Windows OS basically.
How do you spell that?
W-I-N.
Okay. Use Wine to install Windows. To install. Is it a virtual machine? It is a virtual machine, right? To install Windows or VMware Workstation. Station. Okay. So save. And that's going to make your life easy. Again, it's not going to affect any performance. It's not going to slow down your computers, anything like that. You just shut down the VM, everything's gone. It's not going to use anything. And when you bring it up, you can tell to VM to use 100% of resources of your computer. So when you open the Windows machine, then your Mac's going to go slow, but you don't need it at that time because you're on Windows. You finish your work, then you shut down, and your Mac goes to its good old boy that it was before. So it's a good idea to do so. So by next time that you're coming, that is next week, I expect you have your MySeneca accounts will work. You're going to have a Matrix account and everything, so we can actually start working in a lab. Okay? So keep that in mind. That Git book, it's a good idea to go through the first 2 chapters. If you don't even understand it, just understand it perfectly. Just read it to have an idea. So when I do something over here, don't get confused. And if you actually start using it, it would be amazing. It would be amazing for you. All right, so timeline. Computers, information, and compilers. That's what we're going to talk about today. The next day you're coming in, I'm going to actually create a program for you. You'll see how it works, and I'm going to run it to see for you, kind of demonstration of how things work. Essentially, what is a computer? A computer is kind of an intelligent, I just screwed it up right from the beginning. It's the most unintelligent, dumb thing that you can ever see. That's a computer, okay? Computers are logical, dumb beings that we create. So they follow our instructions to the point, right to the dot, and execute those instructions. And if those instructions are designed properly, we're going to see something good happening, okay? It's like you're writing a recipe to make steak, okay? If you write a good recipe, you're going to have a delicious steak afterwards. If you write a bad recipe, you're going to have an awful steak afterwards. So it's your recipe that dictates how things are going to happen. Every single computer has an entry portion, an input part that gets information from you, and based on what you're doing, based on the input that it receives, it generates an output for you. Now, computers used to be much easier to teach because, like, I could actually give you a sample of a little computer, and the computers were like a single-sided type of one-feature type of thing. You had the monitor, you had the keyboard, you wrote a program, that program ran, and your computer worked, and you worked through it. But now the cell phone that this gentleman has over here right now is probably hundreds of times more powerful than a computer that I had when I was a student, okay? And it is a computer. And computers these days, they don't have only one input. You have so many different ways of receiving information, processing them, and generating results, outputs. Now, the output could be the phone ring and you answer. The output could be a movie that you're watching. The output could be basis of a calculation. The output could be the result of how much credit you have, or your credit is bad. Anything, or you need to your I don't know, X-rays ready at the doctor's office. These are all the things that comes out. And the thing is that they all come out at the same time. It's very possible that a computer parallel process on certain thing and does 5 things at the same time, because these days you don't have a computer with one brain. How many cores your computer have? You know? How many cores does it have? Do you know?
This
Yeah.
I don't know about this. My PC at home has quad core.
Quad core, and that quad core is like, when you look at it, the cores inside, they have lots of arithmetic and logical units inside. So when you actually open up to see the task, you're going to see 16 CPUs are working at the same time to do something. And now graphics cards, the graphics card that you use, they have like 4,000 small CPUs over them. That's why it's so realistic when you shoot that guy in the head and the brain goes everywhere. Okay, that's only possible with that, although we use it for that reason. But these days, graphics cards are used for many different things at graphics. For example, mining for a Bitcoin. Okay, you put a computer at home, you put 6 graphics card on it, and you start mining Bitcoins on it, and the graphics card are not doing anything about graphics. They're just deciphering and ciphering Bitcoins or other crypto currencies that we have. Okay, so it's like that. That's what a computer is, and depending on how powerful your CPU is, your computer can work faster or slower. But not only that, computers, to be able to do something at all, they need to have a space to hold the stuff for processing. Okay? And those things are called, anybody? Memory, right? The bigger the memory is, the more your computer can remember at a certain point of time, and as a result, it can be faster. Okay? So you can have an extremely fast CPU, but because your memory is too small, it's going to be small. So the bottleneck becomes the memory. Or you have lots of memory, but the CPU that you have is not that strong enough, so half of your memory is never used. So a balance between the two makes your computer better and faster and everything like that. When you actually receive information, get information into a computer, it works as simple as you see right over here. Let me just bring up a good diagram when I'm actually talking about it. Yeah, so input, well, when you get the information in the input, so information comes through the input, and right from there it goes into the memory, from the input goes into the computer. It actually goes into the memory, and here is actually a CPU. We have a CPU right over here. The hardware that you see is the CPU. So the information is actually passed between the memory to the CPU and back. And when it's done, and it's all based on the instructions that the program actually gave to it, and as a result, an output is happening. So the instruction that you're writing over here is the program that you're learning what to do with, how to write stuff. You write the instructions, you put it in a computer, the computer starts running based on your instructions, gets the input, puts it in memory, back and forth to the CPU, output is going to be the result. As a result of this, anything that you do in a computer is based on the instructions you have written. A computer cannot make a mistake. It's incapable of it. A computer is incapable of making a mistake. Mistake is always coming from you. So anytime that you said, my program crashed, stupid compiler, that's not the compiler, you did the wrong thing. Okay, so things like that. So remember that. So always remember, the source of problem is always the programmer and not the computer. And that's a very important thing to remember. Now, CPU by itself has many different parts. This is kind of a more complicated version of what I just said. Again, when you are thinking about input and output devices, how many different input and output devices you can name? Actually, give me an input device.
Keyboard.
Another one.
Mouse.
Another one.
Microphone.
Another one.
CD.
CD, flash drive. See, an output device. Give me an output device.
Graphics.
Graphics that you see. Touch screen, that's input device. That's input device. so it's not, that's the touch screen. Nobody actually mentioned. I was surprised because usually people the first thing they say is the screen. So these days screen is input and output at the same time. When you're buying something and you're sending your credit card information, that's actually output going out of your computer to the cloud, right? And information coming from the cloud. So the network card of your computer could be the one. The wireless thing that you have is input and output. There are so many different input and outputs, and depending on what you're doing, each one of them is going to get utilized. And that's what you see over there. The CPU by itself has several different bits and places. It has a control unit, a place that it decodes all the code stuff that you have. That is essentially the program that is installed in a computer. A computer is a recursive thing in design. That's the most confusing thing somebody can say. What do I mean by recursive? A tree that you see is a recursive thing. What does it mean? It is built up of itself. Anything that is built up of itself, it has itself inside, that's a recursive thing. If you cut a branch of a tree and stick it to the ground, you have a smaller tree, right? A tree is built up of smaller trees, and you keep cutting until you get to the leaf, right? And that's not a tree anymore, right? It's a leaf. But right before that, it just becomes a smaller tree. A computer essentially is the exact same thing. I talked about the memory that you can have, gigabytes of memory. A CPU by itself is the exact same thing. It has instructions inside a CPU. So actually somebody programmed a program inside the CPU to analyze programs. And that's where it gets confusing. It has a control unit that controls which part is going to do what. It has an arithmetic logical unit that is going to actually check the instructions and act based on instruction, adds 2 by 2 and takes 4 out of it and stuff like that. And it has a memory, actually, piece of memory to write stuff in it and pick stuff from it. But a CPU has only a handful of memory units in it. like a CPU has like 32 registers in it, or 64 registers, depending on how new it is, how recent it is. When I say a register, I mean 8 bytes each. So when I say 32 registers, 32 multiplied by 8. Okay? I'm not saying 32 multiplied by 8 gigabytes. Bytes, 1, 2, 3, 4, 5, that's small. Okay? And it uses that to figure out how things are. But because they are small, they are extremely fast. Memory is exactly like a container for a liquid thing. If I have a cup, I can fill water and I can walk with it, right? When I have a bucket, if I put water in there, I can still walk with it, but slower. If I have a barrel of water, I cannot walk with it at all. So the bigger the memory gets, the slower it gets. It's kind of a thing that it has. Okay? So it's the same thing. Registers, extremely fast, the fastest thing you can believe. Okay? Almost speed of light. It's so fast. But then it comes from that one through another piece of memory that's called cache, and then communicates with RAM, so RAM becomes slower. And from RAM goes to hard drive, and hard drive becomes slower, and so on and so forth. Okay? Of course, now technology is creating exceptions, like when you're having a solid-state hard drive. They say it's a solid-state hard drive, they call it. It's not a hard drive anymore. That's just a memory that you're making it act like a hard drive. A hard drive was a mechanical thing, exactly like old record players with needle on it. But instead of needle, it's a magnet going. Anybody open actually a hard drive? If you open it up, you'll see. I'm not joking. That's exactly what it is. You see plates over there that is turning, and it's the magnetic head going over it, exactly like an old LP player. If you don't know what the LP is, it's a big records, vinyl records like this goes, and you put the needle on it. It works exactly the same way. That's why it was slower. But now they say solid-state hard drives are faster. They're faster because they don't have any moving part anymore. They're just very fast RAM compact in a place. All right. So what is a software? Software is a program that is written to do something. It has a purpose. That's what a software is, okay? Again, a computer is a recursive thing. The basic software that we have in a computer, the very first software that gets into a computer, okay, apart from the CPU that is hard-coded, I'm not talking about that, I'm not going that deep, is the operating system of the computer. Operating system of a computer is a program written by programmers whose job is to manage programs. Okay? What is that phone?
Android.
It's an Android. So the OS on that one is an Android. Who has an Apple here? You have an Apple? That's an iOS. Okay? And if you have an Apple OS, it's probably OS X, or I don't know, whatever they call it. And that OS X is a version of Linux. If I have that one, that's Windows 10. Windows 10 is essentially descendants of the good old Windows that we had from years ago. And anyways, I don't want to talk bad things about it, but it's a crappy operating system anyway. But what I'm saying is that the best operating system, Linux. So all these operating systems, there are programs written to manage the computer. So that's the very first thing goes in a computer. And you turn on the computer. The computer is hard-coded in its nature to look for an operating system, to look for its soul, to find out what am I supposed to do, who am I, okay? I can have the exact same computer as Windows 10 right now. I can go into Linux and shut it down, load Linux, and a computer becomes Linux. A completely Linux box, not a Windows box. And it becomes completely a different type of operating system with different type of behavior. So softwares are very important, and they are all running in RAM. We know that. Now, the input and output that we were talking about as a programmer, when you're actually programming, is in two categories. When you are actually programming to write something, to do something, to make your computer perform certain tasks. When you're doing something like that, that's another type of giving data, inputting something to a computer. Okay? So we have two types of things when we are talking about data. Data could be software, like operating system, like the program you wrote that find out what is the average of 50 numbers. One is that. That's data, that's software. The second type of data is the data that is the outcome of a software running. So you write a program, you finish that data entry, and it's finished. Your program runs. Now it says, I don't know, enter your name, please. And you enter your name, and then at the end it says, hello, John, and it responds to you. So that becomes the data that goes into the software. And essentially, as you see, your program then acts like a computer. Your program has an input, it receives information, and outputs something, and that's going to be your task for the semester. So although we are actually writing our programs on our computers, but our programs are essentially a very minuscule, small version of a computer itself. It does processing, and it goes through information that you enter to it, it processes it, and returns the values needed. Now, we talked about information. How much time do we have? I have enough. Just enough. This is not a slide I'm not putting up for you to show you something, just for me to remember what to tell you. So you don't need to look at that. Okay. How information are kept in a computer? How is it actually kept in a computer? Information are essentially kept in switches. Switches that you turn off and on the light with. You just go on and off. Information are kept like that. We have very small switches in computer, and each switch goes either on and goes off, correct? So how many different how many statuses, how many different states a switch can have? It's either on or off, right? So that's essentially holding two things. Okay, I can actually put some kind of a switch, and I say when I turn it on, if you see the light is on, it means I'm home. If the light is not on, it means I'm not home. So you can actually communicate with others with that. Or I put something in my office. Take a look. If the light is on, I'm in the office. So I can hold information like that, right? Now, if I put two switches beside each other, how many different states I can actually hold? I can hold 4. Why? They can be both on, okay? They can be both off. This one on, this one off, and this one on, this one off. So 4 different situations, right? Essentially 0, 1, 2, and 3. Correct? So, no, 0, 1, 2, 3. Remember, as of this moment, till the day you die, the first digit is 0. Okay? When I say something number 1, what is its number? 0. Remember, something number 2, what is its number? 1. Always remember that. Okay, this is something that we have to remember. If I have 3 digits, if I have 3 switches, how many different things? 2 to power 3, 8. Okay, if I have 4, 2 to power 4, 16, right? So they said, I'm going to pack these switches and start labeling the alphabet with it. So when they put 4 switches, if I can put 4 switches, how many different states? 16, right? That's not enough for alphabet. How many things we have in alphabet? We have 20-something, right? 20? 26? 26. And we have lowercase and uppercase, so it goes 52. Then we have numbers, 1, 2, 0, digits, 0, 1, 2, 3, 4, 5. So 10 over there, that's like 66. We have punctuations. We have open curly bracket, close curly bracket, dot, semicolon. So all those things, they're something like 100, right? So we have to get there. So 4. If I do 5, 2 to power 5 is 32. 2 to power 6 is 64. I'm getting close, okay? And then 2 to power 7 is 128. Done. That's enough. Okay? So that was the first thing that happened. So they had 7 digits, but they said, wait a minute, 7 digits, if I want to have this together, it's difficult to divide. Because it's 7, right? If I want to divide it by 2, one has 4, the other one has 3. Which one I put 3 and 4 in? Can't do, right? So they actually put 4 in each and say, the heck with it, we're going to make it 8. So that became 256 different positions. And that's, ladies and gentlemen, oh, there is no ladies over here, are there? Gentlemen? Okay. This is the first time, actually, in I think 30 years that I don't see any ladies. That's interesting. Wow. Okay, 20 years I'm teaching this, never had a class like this. Okay. All right, so what happens is that, what I was saying is that, so gentlemen, that's how a byte got created. They actually had a byte, okay? But because it was only the first 7 digits that they were taking care of to be able to pass the alphabet stuff that they had, that's the first version of it now. And then later on, they started adding the second language and some more graphics and stuff. It became a byte. So they said, okay, so if we are actually holding, a character that's 7 digits, but if I'm actually using a byte as a value from 0 to 255, then it's going to be 8 bits, okay? And that's how text and binary came to the discussion. So anything that you see, old computers like Windows still deals with text and binary. Why? Because it still thinks text is 7 bits, and when it's the whole byte you're dealing with, it's 8 bits. Where if you're on Linux, there is no difference. Everything is a byte. We don't have a 7 and 8. That's why later on you're going to see if you're transferring something from your Windows platform to a Linux machine, you have to make sure that you select the type of the file that you're passing. If it's a text file, you have to say this is a text file. If not, you have to say so the transfer happens properly. But anyways, so that's how it happened. And the smallest unit of memory got created. And the smallest unit of memory could go up to from 0 up to 255. And they said, wow, we can actually point those things to numbers. So we can actually say when all the bits are off, we're going to put 0. If the first one is on, we're going to make it 1. And the same thing, and it keeps, and the binary representation came out. So essentially, everybody knows over here what an integer is, right? Do I need to explain what an integer is? If anybody doesn't know what is an integer, please tell me, because it means 15 other people don't know either, and they don't want to say it. We know what an integer is. Whole words, right? Whole numbers. They don't have 0.5. 1, 2, 3, 4, 5, right? These are integers. So they said we can actually use this for integers. So to hold the smallest cup, you go to Tim Hortons, the smallest thing that you can get is small cup, right? Then you put small, and then you have medium and large. So the smallest cup for an integer in computer can hold from 0 up to 255. And not more than that. It means if you put 256 for it, it will overflow. You can't do that. Okay? It goes right up to, so that's the smallest cup that you can get. But coincidentally, because that byte, that 7 bits, were set to tag alphabet, they call that small character. That byte, they call it a character. It's not a character, it's an integer. It's from 0 to 255, but because these numbers were initially used to tag alphabet, and they call it ASCII code, to do that, then they call that one a character. So when we say character, we essentially mean an integer that is capable of holding from 0 up to 255. Now, you're going to say, what about negative numbers? Well, they say, if I want to tag negative numbers, then I'm in trouble. Why? How many fingers? 10, right? If I want to tag integers with this, I can go from 0 up to 9, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. If I want to have negative numbers, then what am I going to do? Let's start from minus 5. Minus 5, minus 4, minus 3, minus 2, minus 1, 0. 1, 2, 3, 4, correct? So if I want to use the 10 fingers to tag negative numbers too, I can go from minus 5 to positive 4, correct? The exact same thing happens with characters. If you want to hold negative numbers in a character, then you have to start from minus 128, and you can go up to positive 127, not more. If you go less than minus 128, put minus 129, it overflows. If you go 128, it overflows, depending on what you're dealing with. Okay? Now, they put 2 of these together, and they called it a short integer, which means now it's 16 bits. they put two integers together, two bytes together. So it went up to minus 32,000 up to positive 32,000. Then they made it 4. Then it became bigger. Minus, I think, 2 billion up to positive 2 billion. Then they made it 8. They put 8 bytes together. It became 64 bits. Huge amount of integer number can go in there. Okay? And they do all the math that they want using these. And this essentially means how you hold values in a computer. So whenever you are holding the character A inside a character, are you holding an A in there? No, you're simply holding the number representing A. That is 65. 65. The number 65 inside, it means the 65th sequence in those digits. That's the one. It's number 65. It's not actually A. So if you actually add 1 to it and print it, it becomes B. If you add another 1 to it, you print it, it becomes C, because it's just numbers, right? Are we okay down to here? And these are information. And how we keep them. But when we get to floating point numbers, then we're going to have problem. I'm not going to go with that to tell you how it's done, but all you need to know is that floating point numbers are kept in scientific notation, which means the numbers are huge. Okay, floating point numbers are essentially the ones that have a decimal point, 1.35. Okay, it's not whole numbers. They are kept in scientific notation in a computer. So essentially, it uses two integers. What is a scientific notation? When you do scientific notation, you write something like this. You write 2.56 multiplied to 10 to the power 7. Right? That's a scientific notation, right? So essentially, this means 2, and then it becomes 2, 5, 6, and 1, 2, 3, 4, 5. This is the number, right? That's a scientific notation. It's kept like this. So over here, you essentially have two integers. You have 2, 5, 6, and you have 7, right? So it puts 2, 5, 6 in one integer and 7 in another integer and keeps it in a computer, okay? That's why extra process is needed for not whole numbers. And the old computers, they used to have another CPU called coprocessor. Their job was to be able to actually do stuff like that. Because they're not regular integers, they have to do processes should happen. Anyways, now they use these integers. They use these integers to actually these values to actually see where the information is in a computer. So the old computers that we had, they use 4 bytes. That is essentially called integer, one word, one integer. It's called one integer. That one was used to actually keep the sequence number of information inside your RAM. A RAM is essentially a series of bytes back to back, right? Your RAM is essentially a chain of bytes back to back. So if you want to actually see what goes where, you need to know on 50,000th byte, I have this information. For that, they use 4 bytes. So old computers could not have memories more than 4 gigs because they couldn't, because that was the maximum address. They make it bigger, so the memories got bigger. Those things called addresses. So whenever you're talking about address, it essentially means the sequence number of byte in the RAM of your computer. Okay? That's all it means. Remember that. All right? And they are simply integer numbers. So when I say address of something, don't think that it's like 32 Yonge Street. When I say address of something, it means an integer number. One number that is referring to something. And this is all just information that you need to know. It is physically impossible for me to go through every single thing that we have in these. So your job is later on to go and review it. And by the way, the next day you are coming in, I'm going to put over here before, because I'm going to talk and I'm going to forget. So types, simple calculation, expressions. We have quiz on those. Okay? So the next day you're coming in, you have to study those 3 things. Types, simple calculation, expressions. You got to go through them. Very simple quiz just for me to see if you actually read it or not. I'm not going to ask you complex stuff. Okay? Quickly, I'm going to mention something to you because we have only 15 minutes. I'm going to explain what compilers are in 15 minutes. Quizzes, because everybody's going to say, that's not fair. You didn't teach it and you want us to have a quiz on it before you teach it. I make it fair. How do I do it? There is something called the reflection that you're handing with every single at-home section of your workshop, which essentially you are mentioning over there, I understood this, I had problem in this, you essentially talk to us. I did this workshop, and when I did this, this was the problem, or we asked you a few questions. What did you learn about this workshop? How did you, things like, so your answer, you add one section over there called quiz reflection, which means when I give you your quiz back with your marks, okay, in the next reflection, you're going to say quiz 2 reflection. And in over there, you mention what your problems were, your mistakes were, and what is the correct answer. And I'll give you your mark back. Okay? But catch is, I'll give half of your mark back, not the whole thing. Now, if your answer is kind of right, not completely wrong, then your reflection can get the whole mark back. So if I have 3 questions, and you get 1.5 in the quiz, and all your questions have problem, you send me back 3 reflections, you get the whole mark back. Okay? But if you go completely bananas and don't write any answer for it, then you get half of the mark back. Okay? So that kind of is a way that I encourage you guys to have reflection on your quizzes to see where your mistake was. Again, quizzes are super simple. I'm not going to, it's unfair for me to go in depth in those quizzes, but you'll see. If I have an in-depth question, it's always in a quiz about what you learned before. One question maybe only, okay? But the quizzes are always focused on what's next. So, compilers. We have languages in the world, right? I'm speaking in English right now. I could have spoken in some other language, and if you don't know what that language is, you have no idea, okay, what I'm talking about. Essentially, in our brains, we have compilers. Those compilers receive the language that this compiler knows, and it translates it to whatever goes inside brain that I don't know. So when I say, can I have that coffee? Then he's going to understand what I mean. So actually, your compiler compiled that thing in, so on and so forth. Now, computer is a very dumb thing, so they cannot actually give it something to analyze out of our regular vocabulary that we have. So they shorten the vocabulary that we have into a subset, and they create a new grammar for it. So essentially, the programming language that we learn is a subset of English language. But it's much less words, and it has very strict syntax, very strict grammar that you have to follow. And using that, you can actually write a program in C. Okay? Now, the C language that you're learning to program in, it has a compiler. What does it do? What this compiler does? The compiler goes first through your program to see if you followed the syntax properly. If what you are writing over there is correct with respect to grammar and syntax of the language. If everything passes, if your syntax is right, then it starts translating it into zeros and ones, so it goes to those bytes. Then packages it and puts it aside. When all the little programs that you have written are packaged and saved in those little ones, and they're all okay, all the promises are made, all the things that you said you will do, you did, you'll see what I mean when I'm talking about when we get to it. So the program is proper. It packages all those binary files together to what we call an executable. And that executable gets executed, and you see, oops, it doesn't work properly. Because you followed the syntax, you wrote the program, but your logic was wrong. And then you go back again. From the behavior, you see the code that you have written has this problem in it. You go fix that problem, process again. Compile, make sure everything's okay, create executable, run again. Everything's beautiful, but I forgot to put a space between a first name and a last name. Again, you go back, you fix, and then at the end everything is good. You release your program, and the program is used by users. And then 7 years from now, something wrong goes with it, and they come back to you. And they tell you, hey, you wrote this. 7 years it worked perfectly, but you forgot to cover this exception. And this happened. And then you have to go back to your code. And that's the time that you go like this, because you go, ah! You don't know what you wrote where. Okay? That's why every single piece of code that you write, because it's all cryptic, it's a subset of English language. It's awkward. You have to comment it. At this place, I did this. At this place, I did that. Because I have news for you. 10 minutes after you wrote your code, you look at it, you think someone else wrote it. You have to remind yourself of what the heck did I do in here? And I'm telling you that. You're going to do that. And if you don't do that, you're going to pay for it dearly. Because if 7 years pass the course, some code, somebody comes back and tells you your program is wrong, you have to fix it, then you're going to go, what am I going to do? And worse than that, 7 years after the program is wrong, they're going to come back to you, but you are not the person who wrote it. You just got hired out of Seneca. Some idiot wrote the code 7 years ago, then had a problem, you have to fix it. If that idiot did not comment it properly, did not document it properly, you are in deep trouble. And I have news for you again, 80% of us fall in that category. So change the culture. Document your stuff, okay? Because maybe you work in some place long enough to edit your own code, okay? But these days, if you work for a respectable company, if you don't follow the rules, comments and documents and stuff like that properly, if you wrote the program that solves world hunger, they don't give rat's ass. If it's not written the way they want to, they throw it in garbage, or they tell you fix it and then bring it back. That's why we are so strict. In your tests and stuff, I'm very forgiving. Why? Because you have an hour to do something. Of course, you're going to miss this and that. It's okay. As long as you demonstrate, you know the thing properly, but it's not precise, you get your full mark. But in your workshops and your assignment, you miss a tiny thing, we will not accept it, because you have time to sit and work on it properly. Okay? And that's how it is in everywhere. So don't get frustrated with it. That's life. When you go work for, I don't know, Google, they give you a $3,000 documentation on just what are our standards for code writing. That's it. You are an expert programmer. You're genius of geniuses. If you don't follow those rules, you don't worth nothing. Why? Because nobody can maintain your code. It's the most important thing to do. Okay? So let's see what else we have in here in compilers. Machine language, yada, yada, yada. Yeah, C language. C language actually came from Bell Labs. Okay? C language came from Bell Labs. They wrote this program. They wanted to write a program that is compact enough to be able to run in small machines and be fast enough to be able to do the communication properly and quickly. And that program is called B. Then somebody wrote a program that's much more sophisticated and better than that, and say, what should we call it? It was Bell Labs. They called the program B. Now, what do we call this? They call it C. The next logical thing after that, okay? And then they added one feature to it, and they called it C++. Okay? So that's what it is. So the C++ language that all the geeks know and they get big money out of it, it's simply that, okay? In here, read that thing. It's interesting to show you how fast programming languages are. C program, we have programming languages are in different categories. Programming languages are in different categories. How close they are to our language and how close they are to CPU language. Okay? The closer they are to our language, they're called high-level languages, like COBOL. Okay? I don't know if anybody writes programming COBOL anymore, but like that. Like if you actually look at the code of COBOL, it's funny actually. Like it literally says add 5 to the variable and subtract. It actually rewrite in English. Okay? But those programs are high level, but because they are high level, lots of compilation has to happen. And the code that gets generated out of that one, because of all the flexibility in the language, are not optimized. And because of that, they're very slow. Low-level languages, in other words, on the other hand, are languages that we call assembly languages. Assembly languages are essentially, they're not languages. They're exactly CPU language. So a CPU instruction is served for 4 bytes, and it's a code. It does something. So essentially, they get that one, they put a name for it. Add, subtract, jump, things like that. So your code is very difficult to understand. It's literally machine language. They just tag the instructions for you to do something with it. Okay? Those languages are the fastest thing, but the problem is that if you want to write an accounting program in assembly language, it takes 95 years. It's very difficult. You can't do that. So you have to use high-level languages. That's where C language comes. C language is a middle-level language, which means you can make it act like a high-level language when speed is needed, or you can make it a low-level language when speed is needed, or you can make it a high-level language when documentation and understanding is needed, okay, when you want to write. So that's why you do it that way. And we always reuse our code, so that makes our life much easier. Yes?
Practically speaking, do people really use assembly language, or do companies hire people to write code in assembly?
Oh, of course they do. Of course they do. How can I put this in words for you? You don't write an accounting program with assembly language, but you write a driver for a graphics card that controls the multitasking between CPUs of a graphics card, first in C language, then you hack it with assembly.
Right.
So essentially, when I say hacking, don't think of those movies that people go hack government stuff. In programmers think, hacking means modifying. That's it. You simply have a code, and the code doesn't work properly, not fast enough, you hack the code. Essentially, every single open source application that you have, you get it, you hack it, you make it better. You increase the security by hacking it. Hacking is not breaking into to steal things always. Hacking is just getting to the code. So,
and this has to be in assembly?
As it could be, yeah. But assembly is very low level, very low level. Like a remote control that does the TV, maybe right, even that. Yeah, you hack with assembly. I don't think many people, many percentage of programmers in the world write assembly from scratch. I highly doubt it these days. Okay, usually they write programs that generate assembly code. Okay, that's essentially what compilers are, right? So that's what it is. Let me see. Yeah, and the final thing that I want to do is to create a Visual Studio application and write the first C program for you in the next 3 minutes. So Visual Studio 2017, after you install it, it opens like this. You open it on any computer. What you do is to go to File, New Project. For every single thing, even smaller application, you have to create a project. In that project, you have your source files. And over there, you have to go to Visual C++. You are writing a C language, but the compiler that's compiling is C++. Remember, C++ is C is father of C++, which means everything that C knows, C++ knows. C++ has additions to C. So any C program can get compiled with C++ compiler, but not the other way. So you select Windows Desktop and Desktop Wizard. You select where you want the project to be. In our case, I'm going to put it in a repository so it goes on GitHub. So write in SNN. The project name, I'm going to call it 01 dash. Today is January 17th. So that becomes the name of the project. I'll click OK. Then you uncheck everything and you check an empty project. Click OK. Don't worry, it's all on YouTube. I have it over there. You can go see it 50 times, and I do it every single time. Right now it's being recorded, so at the end of this session you can see that too. Then you go in the Solution Explorer where everything is. In the source files, you right click and you add a new item, and that new item is going to be code, and it's going to be a code that extension is C, so program.c. And in that program.c you go include standard input-output routines. And then over there, you're going to say, the main thing I want to do is to say, to print in a formatted way, hello IPC, and then go to new line. OK? And then I compile and run it. And 3 years later, it's going to say, hello IPC. Ta-da! I wrote a C program, compile and ran it. OK? And we're going to do this 50,000 times, and you're going to see how everything works. Have yourself a beautiful, beautiful day. Don't forget, you have a quiz the next day you're coming in.